So we've seen that if we have a function f of xy, that the slope at the point x0, y0, f of x0, y0, this could be any point on the graph, the slope in the y direction, if we move in the y direction, we're going to move away with slope fy. In the x direction, we're going to move away with slope fx, both evaluated at the point x0, y0. And we get these two vectors, cross product being this normal vector. So the plane that we get in the vicinity of the point x0, y0, f of x0, y0 has one of these two normal vectors. If, depending which way we cross the vectors, this vector is just the negative of this vector. We could use either. Now point xyz lies on the plane if and only if a vector from the point x0, y0, f of x0, y0 to the point f of xyz is perpendicular to n. Now, again, this plane, the plane shaded by red, consists of all the points x0, x, y, z, and I'm not going to actually draw that, but if I could draw a point here on this plane and draw the vector from x, y, z to this, from x0, y0, f of x0, y0, this point on the surface, the graph, to the point x, y, z, that's got to be perpendicular to the normal vector that we get when we cross these two vectors. That's the geometry of the situation. So I could draw a little picture. If this point represents x naught, y naught, f of x naught, y naught, and this point is x, y, z, then this vector from the known point of our graph to the point x, y, z on the plane has to be perpendicular to the normal vector we get when we cross that vector in the y direction with that vector in the x direction. That is, when we do the cross product of this vector with this vector. And I'll indicate that normal vector, that cross product, this way. And in terms of the picture, this one appears to be going up in the z direction, so I'm going to use this version of the normal vector. It wouldn't make a bit of difference if I used this one. The equation's going to come out the same way. So again, our condition is that this vector be perpendicular to the normal vector. Well, the normal vector is one of these two. This vector is just x minus x naught I plus y minus y naught j plus z minus z naught k, where I've used z naught instead of f of x naught minus y naught. Just using this notation for convenience, we'll fix that in a moment. I just noticed an error down here. We'll get to that in a minute. Okay, well, that vector then is this. We dot that with our normal vector, and we get this. And this is the equation of our tangent plane. Now I had a plus down here because I was writing carelessly, so I'm going to replace that by a minus because clearly the Fy is negative. And if we want to put this, well, let's just put the qualifier that z naught equals f of x naught y naught. So we know where z naught comes from. This means we can choose any point x naught, y naught in the xy plane, evaluate the function at that point, and call that value z naught. That gives us a point x naught, y naught, f of x naught, y naught, or x naught, y naught, z naught on the graph of the function. Point x, y, z is on the graph, provided this vector is perpendicular to the normal vector that we previously calculated. And this is not a formula to be memorized. This is a process to be understood. The whole idea is simply that any vector between points of the plane has to be perpendicular to a common normal vector, and it's important to understand this through the geometry.